1985 AB31 says that the volume of the cone, given by this formula over here, it says the radius and the height are both increasing at a constant rate of 1/2 centimeter per second. So again, when quantities are increasing in number or increasing in value, their rates of change are positive. So I want to make sure to keep that in mind, is that when you do get one in which the rate of change is negative, then if the quantity is getting smaller, then its rate of change is negative. So again, this one is laid out nicely for us, and if we have the ability to differentiate using implicit differentiation, then we're good to go, because you're given everything. You're given dr dt, dh dt, and you're given what you want, volume in terms of rate of change in terms of h and r, and you've got it all laid out for you. So hopefully this is a good example for reminder of how to do our implicit differentiation. So we know what we want. We want our dv dt, and so we're going to differentiate both sides with respect to t. And I'm going to take this little steps here, okay, so that you all know exactly how to do this problem. Okay, don't try to do too much in your head here. You're going to get yourself into trouble. All right. So one thing I like to do is if I have a pretty complicated expression that I'm differentiating, then I want to take out any constants to kind of simplify the process a little bit. So that's exactly what I'm going to do here. I'm going to take the 1/3 pi out, and I'll write it as pi over 3. And then I'm going to multiply that by the derivative of r squared h with respect to t. Okay? And I urge you to take these little baby steps here, okay? Because this is where students tend to have make the most mistakes, not recognizing that this is the product of two functions. And when you take the derivative of the product of two functions, you have to use the product rule. Well, unless you can rewrite it, but in this case we're needing to use the product rule. So the derivative of r squared h would be the derivative, or let's do this, the first times the derivative of the second, so r squared times dh dt, plus the second function, which is h, multiplied by the derivative of r squared. And I'm going to even take that, I'm going to rewrite that this way, and so it's like a really baby step here, because I could have done the derivative of r squared I could have done that all in one step. So we have r squared dh dt plus h, and now let's just focus here on the derivative of r squared with respect to t. Well, that's 2r, 2r times dr dt. Okay, so hopefully by me doing little steps at a time, you can see exactly where things are coming from. And now it's just a matter of plugging in the right values and not making careless errors. Okay, so let's do that in a different color. In fact, I'll scoot over a little bit here. Let's scoot over here. Equals, does that mess you up? No, that's okay. So we have equals pi over 3, that's on the outside. And on the inside it says we want dv dt, remember, so that's still what all this stuff on the right side is equal to. It's dv dt. Okay, well, let's be really, probably didn't do this in the last video. I get kind of lazy on this, and I'm sorry, but dvt at the precise moment when the height is 9 and the radius is 6, is that what we have? Yeah. Alright, so now we can plug in the r and the h. And I want to reiterate something, that you're not allowed to plug in any values that are changing throughout the problem, right? So we have a rate of change of something. So these values r and h are changing throughout. They're not constants. They're only constants for a moment. And that's, remember what we talked about, that moment in time when we find the rate of change of something. Well, that's calculus, that instantaneous rate of change. Well, again, h and r are only 9 and 6 for a split second, or just a moment in time. Not even a split second, but a moment in time. Okay, so now just to reiterate though, that you just don't want to plug in your r and your h, your 6 and your 9, into the original equation for the for the volume. Okay, so hopefully that sticks with you. So the r, we're going to replace r with 6, so we have 6 squared. Remember the dr or dh dt, that's 1/2. The h is said, that's what we want to find the dv dt when h is 9. We're going to substitute again our 6 for our r, and again a 1/2 for the dr dt. Do I have enough parentheses there? I think I need one more. Alright, 1, 2, 3, 4. 4 lefts, and 1, 2, 3, 4 now, 4 rights. Alright, so then another color, pi over 3. Now we have 6 squared times 1/2, so 6 squared is 36 times 1/2. Well, 36 divided by 2 is 18. So there's going to be an 18 right there. Okay, plus, it's got to be careful here, there's a lot of numbers floating around. And you have 6 times, oh, you got the 1/2 times 2, well, that's just 1. And so we have 54. 9 times 6 is 54. And you can see that I'm looking at the problem here, and I see 54 pi. Okay, so I see, so like I said, I see 54 pi, and so if you make one little error there, you're gonna get 54 pi. 54 and 18. Even even though I can do that in my head, I don't want to take any chances. 4 plus 8 is 12. Carry the 1. I get 72. Okay, and I have a pi times 3. Pi over 3, or times 72, sorry, and then I have 3 going into 72 24 times. Okay, and all that being said, we see that the answer is 24 pi, and 24 pi is C, and that's the answer. I like it better with a green C with a red box. Okay, there we go, as holiday season is approaching. Anyway, there you go.